We are looking at a brand new paper today titled Distilled Reinforcement Learning for LLM Post-training. It's by Chen Wang alongside researchers from Nankai University, Zhongguancun Academy, and several other institutions. And if you're running any sort of alignment or reasoning pipeline right now, you already know post-training is currently kind of deadlocked.
Oh yeah, absolutely deadlocked.
Right. You either use standard reinforcement learning, which, gives you these coarse sequence level rewards, but really struggles to teach entirely new knowledge, or you use on-policy distillation, or OPD.
Right, which gives you that dense token level feedback via KL divergence.
Exactly. But the problem with OPD is that it forces the student to unconditionally mimic the teacher. And that imitation, it breaks down completely if the teacher and student have different architectures.
Yeah, cross-family setups just destroy it.
So this paper proposes a third path, which they call Distilled RL. It's a unified framework that directly injects teacher logits into the RL gradient. And they do this using three really specific mechanisms. You've got reverse importance sampling, negative sample reset, and sequence-level geometric normalization.
And the results they got are just massive. Huge gains in cross-family distillation, plus you get these sustained training improvements without the premature saturation that usually just, plagues distillation setups.
It's a huge deal. Oh, welcome to AI Paperslop, by the way. This is our YouTube series where we summarize the latest AI and tech papers so you can stay at the absolute cutting edge.
Glad to be here for this one. The reason this new framework is so necessary, well, it becomes really obvious when you look at the fundamental limits of how we currently handle credit assignment in post-training. Take on-policy RL algorithms, like PPO or GRPO. Generating trajectories from the current, evolving student policy naturally mitigates that distribution shift between your training environment and inference, right? You evaluate a response, calculate an advantage score, and then update the policy.
But let's say the model outputs 1,000 token chain of thought for a math problem. It arrives at the correct final answer, and it gets a positive sequence level reward. The RL objective doesn't actually tell the model which specific intermediate tokens were the actual strokes of genius.
Exactly. It has no idea.
It could be that 90% of that chain of thought was just useless filler, and the model only figured out the core logic in a single sentence at the very end.
Yeah, and because that supervision is so incredibly sparse, RL is just highly inefficient at teaching the model novel reasoning pathways. It reinforces behaviors the student model already somewhat knows how to do.
Right, it's just rewarding what's already there.
Yeah, pulling the model out of its existing capabilities to learn something entirely foreign, it just requires this agonizingly massive amount of exploration.
So naturally, the obvious fix is to give the model dense token-by-token feedback, which is basically the entire premise of on-policy distillation, right? OPD.
Yep, OPD.
Instead of waiting for a binary reward at the end of the whole sequence, OPD minimizes the KL divergence between the student's output distribution and the teacher's output distribution on the specific states the student actually visits.
It provides that localized feedback that standard RL completely lacks. But, the authors highlight what they call a fundamental dilemma with OPD that makes it, fundamentally unscalable.
Okay, lay it out for us.
So let's look at the two possible setups. Scenario one. The teacher and the student are architecturally similar, and they have pretty similar capabilities. Minimizing KL divergence here, it gives the student almost no new... Exactly. But scenario two is where it really falls apart, and that's the cross-family setup. Imagine you have a Quinn teacher and a DeepSeek student.
Oh, wow. Yeah.
Look completely different. Their underlying reasoning distributions, their initializations, even their vocabulary mapping, they are fundamentally different. So forcing the student to unconditionally minimize KL divergence and match the teacher's distribution token for token, it just creates this incredibly noisy, fractured optimization landscape.
Because the student is trying to contort its own internal logic into a shape that just doesn't fit its own architecture at all.
Yep.
But wait, KL divergence is basically the gold standard for distillation, right? Why is matching the teacher's distribution unconditionally such a bad thing?
Well, even if it manages to do that contortion, unconditional KL imitation converges way too fast. It traps the student in a local optimum that's dictated entirely by distribution matching.
I see.
Once the distributions are close enough, the loss just drops, the gradients shrink, and there is literally no room left for subsequent reward-driven exploration. It hits a ceiling.
So this premature saturation is essentially the teacher becoming an anchor, that holds the student back.
Exactly. The moment the student mimics the teacher sufficiently, learning just stops, regardless of whether the actual task performance is optimal or not.
That is a massive problem. So the solution the authors propose, Distilled RL, they basically abandon that separate KL divergence loss entirely, right?
Yeah.
They just integrate the teacher supervision directly into the RL objective.
That's the secret sauce, and the core engine driving this is what they call reverse importance sampling.
Reverse importance sampling. Okay, break that down.
Well, in standard off-policy RL, you measure the ratio between the new student policy and the old student policy to keep updates stable, to prevent the model from shifting too far in a single step.
Right, pretty standard.
But Distilled RL changes the numerator. It calculates a token-level ratio comparing the teacher policy to the old student policy.
So it's measuring the relative preference of the teacher for every single token the student generated.
Yes. Mathematically, it evaluates the probability the teacher would have chosen the action the student just took, divided by the probability the student originally assigned to that swing action.
Oh, that's clever. It's basically a token-level reward-shaping mechanism. Like, if standard RL is just a teacher stamping a binary A or F at the top of an essay, this reverse importance sampling acts like a highly specific highlighter.
Oh, I like that analogy.
Yeah, the teacher's taking a highlighter to the specific logical steps it preferred, scaling the gradient of the final task reward based on that localized probability mass. The student is still graded on its own original essay. It's still optimizing for the final verifiable reward, but the teacher's logits are guiding the path it takes to get there.
Spot on. And they also clip this ratio, which is very similar to standard PPO clipping, just to prevent unstable gradient amplification.
Right, because if the teacher assigns a near-zero probability to a token the student generated, you don't want the gradient to just completely explode trying to reconcile that extreme likelihood mismatch.
Exactly. You have to keep it bounded. But applying these token-level ratios broadly actually destroys the RL objective if you aren't extremely careful with the math.
Which brings us to the mathematical guardrails. There are two big ones that make Distilled RL actually function, starting with the negative sample reset.
Right. So this teacher-based reweighting is only applied to responses that achieve a positive advantage, meaning the trajectory actually worked and achieved a reward higher than the group average.
Okay.
If a sample has a negative advantage, basically a failure, the teacher weight for that trajectory is reset exactly to 1.
Wait, hold on. This feels completely counterintuitive at first glance. If the student generates a terrible response with a negative advantage, isn't that the exact moment you want a smarter teacher's logits to step in and correct the behavior?
You'd think so, right?
Yeah. Turning the teacher off when the student fails just sounds like a massive missed opportunity.
But the math trap here is fascinating. Look at the gradient update equation in RL. A negative advantage acts as a penalty. The gradient pushes the model's policy away from those specific tokens.
Right. Standard RL penalty.
Now imagine a failed negative advantage trajectory where, purely by chance, the student generated a few intermediate tokens that the teacher actually preferred.
Okay, so the teacher-to-student ratio on those specific tokens is greater than 1.
Yes. Multiply a negative advantage by a ratio greater than 1, and that negative number becomes even larger.
Oh, wow.
The student receives a larger penalty for a token the teacher actually wanted it to generate. You are mathematically forcing the model away from the exact behavior the teacher is trying to encourage simply because the overall sequence failed.
That is wild. You're literally punishing the student for taking a step in the right direction just because they happen to trip at the finish line.
Exactly. And on the flip side, if the teacher doesn't know how to solve the problem either, its supervision on a failed trajectory is just adding pure noise.
Right. So reverting back to standard RL by resetting the ratio to 1 for negative advantages, it's just this incredibly elegant way to prevent the distillation signal from accidentally acting in reverse.
It ensures the distillation is strictly additive. Now, the second guardrail addresses a scaling problem that happens even on the successful positive advantage trajectories, and this is the sequence-level geometric normalization.
Yeah, we have to remember how autoregressive generation works here. We are multiplying the probability of token 1 by token 2 by token 3 all the way down the sequence. And we are evaluating the teacher's probability on tokens that were sampled purely from the student's distribution.
Right, which means the teacher is inherently going to assign lower probabilities to these tokens than the student did.
Simply because it's an out-of-distribution sequence for the teacher.
Exactly. Consequently, the teacher-to-student ratio is frequently going to be less than 1.
And when you multiply a sequence of hundreds of ratios that are all less than 1, the global product shrinks exponentially towards zero.
It just vanishes. Even if the student generated a brilliant positive advantage trajectory, the overall gradient weight basically disappears just because the teacher has a slightly different vocabulary preference.
So how do they fix it?
Distilled RL fixes this by dividing the raw token level ratios by their sequence level geometric mean.
Okay, math time.
Yeah, taking the geometric mean, basically multiplying all the ratios and taking the nth root based on the sequence length, it gives you the average decay factor for that specific trajectory.
Right, so by dividing each individual ratio by that geometric mean, the overall product of the sequence multipliers perfectly equals 1.
Yes. You are redistributing the credit internally across the sequence.
So the tokens the teacher liked relatively more get a boost. The ones it liked relatively less get suppressed. But the absolute scale of the global RL reward remains entirely unchanged.
Exactly. It isolates the relative token level preferences from the absolute scale differences between the two models. This completely prevents the gradients from vanishing while still preserving that dense token level supervision.
Okay, I mean, the math is airtight, but there is always a gap between a clever loss function and actual real-world knowledge transfer.
Oh, for sure.
To prove that the student is genuinely absorbing the teacher's abstract internal logic and not just, finding a slightly more efficient way to brute force the RL rewards, the authors designed this highly interpretable case study using policy entropy.
Yeah, they call it the Entropy Thermostat, which I love.
It's a great name.
To completely isolate the distillation mechanism and remove confounding variables like model scale or architectural mismatch, they actually use the student model as its own teacher.
Oh, that's smart.
Yeah. Policy entropy essentially measures how uncertain or soft a model's distribution is across its vocabulary logits.
Okay, so how did they run the experiment?
They set a target policy entropy of 0.5. If the student's entropy rose above that threshold, meaning it was getting too uncertain, they swapped in a low temperature 0.8 teacher.
Because lower temperature makes the teacher's distribution much sharper and more confident.
Right. And if the student's entropy dropped below 0.5, becoming too rigid, they swapped in a high-temperature 1.2 teacher to soften the distribution.
It really is like a thermostat for model confidence, continuously nudging the student back to a target zone.
And by continuously toggling the teacher based on the student's state, they created this dynamic feedback loop driven entirely by the reverse importance sampling mechanism.
So what happened?
The student's entropy rapidly moved from its initialization point straight to the target region. And then it visibly fluctuated back and forth perfectly across that 0.5 threshold, responding dynamically to the shifting teachers.
Wow, it tracked the teacher's internal state perfectly.
Perfectly. This proves Distilled RL doesn't just pass along a task completion signal, it successfully transfers abstract distributional properties from the teacher's latent space right into the student.
That's incredible. And didn't they also run an ablation study on this?
Yeah, they did. They ran an ablation on this specific setup to test the necessity of that negative sample reset we talked about.
Right, the counterintuitive guardrail.
Exactly. When they removed that mathematical guardrail, allowing the teacher to reweight negative advantage trajectories, the student's entropy just flatlined well below the target. It completely stopped responding to the temperature shifts.
Because the distillation signal inverted on itself, just as the math predicted, completely suppressing the knowledge transfer.
Yep. Seeing that theoretical trap proven in an isolated ablation study gives a lot of confidence going into the actual state-of-the-art benchmarks.
So let's get into those benchmarks, because this is where the rubber meets the road. They use the EZR1 and VRL frameworks, relying on the Qwen38B GRPO model as the static teacher, right?
Correct. And they ran this across an absolute gauntlet of mathematical reasoning and general knowledge benchmarks. We're talking AME 24, 25, and 26, CMIMC 25, GSM 8K, Math 500, and MMLU Pro.
Testing on AME and CMIMC is super crucial here because those are long horizon reasoning tasks where standard RL credit assignment struggles the most.
Exactly. And they deployed two different student models. The within family test used Qwen34B, but the real stress test, the one everyone cares about, was the DeepSeek R1 Distill Qwen 1.5B model.
Okay, let's just call it DSQW 1.5B for sanity.
Good call. So DSQW-1.5B is the ultimate cross-family challenge. You have a Qwen teacher and a DeepSeek student. They have completely different initializations and wildly divergent reasoning distributions.
So how to do?
On that cross-family setup, the base DSQW 1.5B model scored an average of 31.7 across the math benchmarks. Standard on-policy distillation pushed it to 35.2, and standard RL got it to 36.8.
Okay.
Distilled RL jumped the average score to 40.0.
Oh, wow. 40.0. That's massive.
It outperformed both baselines by a significant margin. But analyzing the training dynamics over time reveals exactly why Distilled RL achieved those numbers.
Right, because with standard OPD, the training graphs show the model plateauing very early in the run.
Yeah, the KL divergence traps the model in that local optimum we discussed earlier. It just stalls out.
A common workaround people try in the field to fix that is simply adding the two losses together, right?
Yeah.
Calculating the standard RL loss and just adding the standard OPD KL loss on top of it.
They tested that too. They ran an OPD plus RL baseline, and the resulting training graphs show a consistent performance decline in the later stages of training.
Wait, a decline?
Yeah, the gradients actually begin fighting each other. The KL divergence is trying to hold the model in a state that mimics the teacher, while the RL signal is trying to pull the model out of that state to find higher task rewards.
So the resulting interference just degrades overall performance.
Exactly. And they also tested whether standard OPD's failure was just like a sampling variance issue by increasing the rollout group size from 1 to 4 and up to 8.
Did that help?
Scaling the group size did absolutely nothing to improve OPD's final performance, which proves the bottleneck is the KL objective itself, not variance.
Wow. And Distilled RL, in contrast, showed a sustained, unplateaued upward trajectory throughout the entire training run, right?
Yep. Because the teacher is only guiding the gradient of the RL objective rather than enforcing a separate restrictive constraint, the model literally never stops exploring.
That's the dream. But, there is a critical limitation to this framework that the authors explicitly note, and we should talk about it.
Yeah, we have to. Distilled RL relies on evaluating the teacher's probabilities on trajectories generated by the student.
Right.
Meaning we are operating under the blind assumption that the teacher is actually competent enough to solve the specific prompt the student is attempting.
Because if this student wanders into a highly complex, uncharted reasoning pathway that the teacher just doesn't understand, the teacher might hallucinate its probability distributions.
Exactly. And the reverse importance sampling math treats those hallucinated token preferences as absolute ground truth, which could potentially inject garbage logic directly into the student's gradient.
That sounds dangerous, though I guess the negative sample reset partially shields the model from this, right?
It does, yeah. If the teacher's garbage logic causes the trajectory to fail and achieve a negative advantage, the reset drops the teacher's weight to 1, reverting to standard RL.
Right. But on successful trajectories, a hallucinating teacher could still subtly degrade the quality of the student's reasoning pathways.
It's a real risk.
Which honestly sets up a fascinating puzzle when you consider the late stages of post-training. Since Distilled RL uses a static teacher model to guide a dynamic, constantly evolving student. Assuming the post-training run is successful, the student is eventually going to mathematically reach a point where it surpasses the fixed teacher's capabilities.
Oh, absolutely. The distributions will eventually cross over. The student will be generating novel, brilliant reasoning trajectories that the teacher inherently evaluates as low probability just because they exist outside the teacher's own latent space.
Right. And when that crossover happens, this highly effective token-level reweighting suddenly becomes an anger. An inferior teacher starts penalizing the student's most advanced leaps of logic.
Which means the next frontier for this framework isn't just better gradient math, but probably adaptive gating.
Right, designing an algorithm that dynamically detects when the student's policy has eclipsed the teacher's knowledge on a given prompt and simply turns the distillation mechanism off.
Just letting pure RL carry the model the rest of the way.
Exactly. So if you're building post-training pipelines, figuring out how to build that thermostat for teacher obsolescence, that is your next major challenge. Get to work.